Get the slideshow ready. All right. Any questions so far? Okay. Last time we were in Chapter 1 still, Systems Linear Equation 1.2, Gaussian elimination and Gauss-Jordan elimination. And we had just done example 7 on page 19, and we're down to the sort of a illustration at the bottom of page 19. So I guess this one's worth looking at because this is more like a real-life type problem where things aren't always as pretty as you would want them to be. Okay? Here's a system of equations. Let me get my pen set up. If I can get it to show up again. There we go. All right. 2x minus 5y plus 5z is equal to 17. Alright, it's not looking good. 3x minus 2y plus 3z is equal to 11. Minus 3x plus 3y is equal to negative 16. Okay. Now, what their point is here, and they do kind of have a point, is that if you allow yourself to be driven by a set rule pattern, I guess you would say, first thing you would do here is divide the first equation by 2, because you want a leading one there. And then you say, well, yeah, a variety of things. Well, yeah, you'll start off having a 1 here, but you'll have a fraction here, and a fraction there. And then everything else will get pretty messy from then on. But it's all doable, okay? What they're saying is sort of be judicious in this. And before you do that, why don't you just look at this one and say, well, there's a couple things we could do. One, and I think you suggested something like this before, somebody did, why don't we subtract this equation from that equation? And that's another way to get a 1 here. And that might be a better way of doing it, okay? Or, the first thing that came to my mind, actually, one thing that came to my mind, if you divide the third equation by 3 or minus 3, I'm going to go with minus 3, then you have a 1, a minus 1, and a positive 16/3. Well, that's a lot better than 3 fractions, because we only have 1. But another thing you might say is, well, wait. Why couldn't we add these two together and eliminate this, and you wind up with a 1y here? You still don't have anything to do with that. Okay, so there's several things you could do. Try to figure out the one that's going to get the best result for the least pain. Okay, I'm lazy that way and going for it. So that's what they're saying here. Let's see what they're saying. It says you may be inclined to multiply the first row by 1/2, produce a leading 1. It will result in that. Sometimes judiciously choosing the order in which you apply elementary row operations enable you to avoid the fractions, and but they don't say how they would approach that problem. So I would try a few things. I'm not going to solve it for you. That's not what they were doing. They're just saying, here's an example. You might try several things. And like I said, at least one that pops in my mind is subtract row 1 from row 2. You know, row 2 minus row 1. And that will give you a 1 in that leading position. And you know you only have integers then. It may be messy later, but at least you start off without a fraction. All right. Now they also have a discovery here. I won't do any more with that one because they didn't in the book either. They just gave it as an example. Let's look at the discovery here. Okay? 2x1 plus 3x2 plus 5x3 is equal to 0. Minus 5x1 plus 6x2 minus 17x3 is also equal to 0. And 7x1 minus 4x2 plus 3x3 is also equal to 0. And it says, without doing any row operations, explain why that system of equation is consistent. What's our definition of being consistent?
That there's no solution, or
if you said there's no solution, that means there is a solution.
right.
Okay, right.
Yeah,
There is a solution.
There is a solution
Right.
that is.
All right, and that's exactly what you mean. There's at least one solution.
Mm-hmm.
Can you tell me a solution for that system of equation?
Let's see.
Without doing any row operations.
All of them could be 0.
Exactly, the trivial solution. x1 equals 0, x2 equals 0, x3 equals 0.
Yeah.
That is a solution, therefore this can't be inconsistent. It has at least one solution.
Mm-hmm.
More than likely it has more than one, but it definitely has at least one. Okay? So that's all you had to do there. Now, then it says the following system has more variables than equations. Why does it have an infinite number of solutions? Okay? Now let me see if I can simplify my writing of this a little bit. I'm hoping to be able to do that. Okay? The first equation is 2x1 plus 3x2 plus 5x3 plus 2x4. And that's equal to 0. Second equation is minus 5x1 plus 6x2 minus 17x3 minus 3x4. And that's equal to 0. And the next one is 7x1 minus 4x2 plus 3x3 plus 13x4. And that's equal to 0. Okay? Now it says here, the following system, that one right there, has more variables than equations. Why does it have an infinite number of solutions?
Because well, not any set of numbers, but because infinite solutions, because there are a good way to describe that. I get what you're saying. Yeah, you could swap the positions of the.
Here's one way to look at it. And this isn't the only way, but it certainly is one way.
Uh-huh.
Let's imagine we do our solve. Well, number one, it has at least one solution, just the same reason as before. The trivial solution, all the x's equal 0, that will give you an answer. So we know it has at least one solution. So this isn't an inconsistent system. So that's the first part. The second part is, let's imagine, we're not going to do it, but just imagine we did row reduction on this. And everything worked out the best it possibly could. Okay? Then we would have a 1 here and 0s below it. Right? Mm-hmm. Then you'd have a 1 here and 0 above and below it. Gauss-Jordan elimination. Then you'd have a 1 here and 0s above it. Well, then you still have a variable here that you don't have a leading 1 for. So therefore, this is going to be a parametric. Okay? And because it is, then you can set that equal to anything, like t, okay? And then all the rest of them, this would be, depending on, which you use, let's just say this came up with a -5 down here. Then you'd have x3 minus 5t is equal to 0, x3 is equal to minus 5t. This could be some other value of t. This would be some other multiple of t. Well, guess what? Then you have your x1 equals something. For any t you choose, you have a 4. In other words, this is I have a name for it. I'm trying to remember what that name is. It's not ill-posed, but it has, because you have more variables than you have equations, there's no way you can solve for each one. Just no way you can do it, okay? So it will have dimensions that you can't deal with. And here's a kind of a weird way of looking at it. This would require a 4-dimension answer. And you only have 3, in a sense, 3 dimensions covered here because you only have 3 equations. Yeah, they deal with all 4 dimensions, but you have some variation there that you just can't eliminate because you need at least 4 equations.
It's almost like superposition. It's like it's describing a superposition.
Yeah, that kind of a concept. Exactly. Okay, so there's your discovery. I guess we discovered something.
We discovered superposition.
All right. So let's do one similar to this, but not quite that complicated. And this will be example 8. 2x1 plus 4x2 minus 2x3 is equal to 0. They're liking zeros now, aren't they? 3x1 plus 5x2 is equal to 1. Okay. Now, where would you begin on a problem like that? And it says use Gauss-Jordan. So what would be your first step to proceed with Gauss-Jordan elimination?
The problem with this is only one example of x3, but to find out which one of x2 are, we can resolve that. I'm tempted to divide the first one by 2.
Oh, absolutely. Well, let's first write it as oh, goodness gracious, man. Augmented. I was always thinking of adjunct matrix. That's not an augmented matrix. So that would be what?
It would be 2, 4 minus 2. Is that a 6 at the end?
It's a 0.
0.
Okay, making fun of my writing. That's all right. I'm not hurt by it. Okay.
3, 5, 0, 1.
Okay. Now, your first statement was, and we'll write this as a matrix with brackets around it, is do row 1 divided by 2. Okay? So that becomes what? 1.
1, 2, minus 1, 0.
Okay? And we'll write down the second row. 3. We'll try to write down the second row. 3, 5, 0, 1. Okay, next step.
So nothing the second row divides nicely by. So if we could try subtracting the. That wouldn't be that great part of it.
That was so ugly, I'm going to change it. Yeah.
I almost feel like the original augmented matrix, the top row, or the second row minus the first row, would yield better results.
It would give an equivalent result, I mean.
Yeah.
I don't know that it's any better, but it would be then a 1, 1, 2, 1. and then you'd have to determine which one you're going to use with that. So that would do. But I mean, this is pretty simple too. What do you want next to happen? You got a 1 in the first position. That's what you wanted.
Right.
What do you want next?
We want a 1.
You want to.
Oh gosh, right now. Yes, it's not showing.
You want it 0 below it.
Yes.
And how do you get that?
So we subtract 3 times the first row.
Yeah.
Which would be
minus 3 row 1 plus row 2.
So
Yeah.
it would be 0.
Okay. Okay. 1, 2, minus 1, 0, and then 0 what?
Minus 1.
Minus 1.
Minus 3.
No, positive 3, right?
Oh, so yeah, positive 3 because it's minus
Right.
times 1. Yeah, that's, and then just 1.
1. Yeah. Okay. I'm going to. I got carried away on my bracket here, so let me get it back to a reasonable size. Okay. What do we want to happen next? You want the first non-zero entry of this row to be a
1.
A 1.
So you can multiply.
Yeah. By negative 1. So that'll be a plus, minus, and that will be a minus. So let me get my eraser here so I can make that a minus. Got it. Okay. What's the next thing we want to happen?
Do you want to subtract the 1 row from another one?
Yeah. We want the thing above that leading 1 to be a 0. That 2 to be a 0. And you get that by minus 2 row 2 plus row 1. Right?
Yeah.
All right. So we're going to leave the second row alone. 0, 1, minus 3, minus 1. And the top row becomes 1, 0.
Is that minus 6 minus 1? No, that's positive 6.
Yeah.
Subtract 1. So that would be a negative 7, wouldn't it?
No.
Or both be
5, right?
Yeah, because the.
Right.
Okay, because it would be. Yeah, you're right. Because the 6 would go down by 1. Yeah, so it would be 5.
Okay.
And then 2 times that minus 1. So that would be minus 2, wouldn't it?
No, positive 2.
Positive 2.
Minus 3 times minus 1, positive
Yes, because it flips the sign.
Yeah.
Sign flipping is always. Woo.
2. Okay. Now, you Gauss Jordan it out. You got leading 1, zeros above and below. Nothing else you can do here.
Uh-huh.
Now remember what the columns stand for. X1, X2, X3, and constants. Okay? So obviously your X3 is free to roam. Okay? You don't have anything to do. These you've identified as something. So here's what we'll do. We'll write down, this stands for the X1, so X1 plus 5. Now, really the first thing you do, since this is free to go, we're going to say let X3 equal some parameter. What's your favorite parameter?
Let's do 0.
Say again?
We do a 0 as a parameter?
0, no, don't use a number.
Oh,
a letter.
Oh, sorry, letter for a parameter. C.
T. Okay, that's everybody's favorite, I think, for a parameter for some reason. So that will be plus 5t is equal to 2. Writing those equations equivalent to that here. So
the last parameter outside of 3-dimensional space is time.
Yeah, well, yeah. But then they use S and T and then S, T, U, V, blah, blah. Yeah, so they back up for the S and then go forward for the rest of them. So this would have us X1 equal 2 minus 5t. And then your X2 here minus, again, let X3 be t. So this would be X2 minus 3t, right, is equal to negative 1. So then I would say the X2 is equal to 3t minus 1. And then we've already said X3 equal t. So basically your solution are actually solutions, infinite number of solutions, an ordered triplet, because you have three dimensions here, you might say. It would be 2 minus 5t, comma, 3t minus 1, comma, t. There it is. Any t you happen to choose, as in 0. That would be 2, 3, 0. Let's see if 2, 3, 0 will work. 2 times 2 is 4, plus 12 would be 14. Yeah. Why does this not work? Oh, no, this is a minus 1. Okay, sorry. 2, yeah, 2 times 2 is 4, minus 4, plus 0 is 0. Yes, that works. And this one would be 3 times 2 is 6, minus 5 is equal to 1. Yeah, that works in any other t you happen to choose. Negative pi thirds over 17. I mean, whatever you want to choose there, put it in for each t, it'll work. Okay. So that's how you get your infinite number solution. Parameter, they chose t as well. They said 2t, x1 equal 2 minus 5t, x2, I like to lead off with the positive, 3t minus 1, and x3 equal t. Okay. Now, it says, note that this example, it looked at two elementary methods, elimination methods for solving a system of linear equations. Which is better? To some degree, the answer depends on your personal preference. In real-life applications of linear algebra, systems of linear equations usually solved by a computer, and most computer programs use a form of Gaussian elimination, not Gauss-Jordan, with special emphasis on ways to reduce rounding errors and minimize storage of data, and because the examples are blah, blah, blah. Okay. Whereas, but doing them by hand, you have to back substitute with Gaussian, which computers can do really easily. But with Gauss-Jordan, you just write down your answer, basically.
Yeah.
So it just depends whether you want to do a little more work up front and do Gauss-Jordan, or minimize the work up front and then do a little extra at the end doing back substitution. Pay your money and take your choice. You've already paid your money, so do whichever way floats your boat. Okay. So let's move on to page 21, homogeneous systems of linear equations, which is exactly what the discovery was in the top of the previous page. And that's how this works sometimes. The discovery is just a little bit before you hit, and they talk about it. Okay? So let's clear this out of the way and explain what in the world we mean by a homogeneous system of linear equations. Systems of linear equations in which each of the constant terms is 0 is called homogeneous. That's what we did in that discovery, and here's the generic way of expressing it. A11 x1 plus A12 x2 plus A13 x3 plus dot 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 plus A1, do they use n or m? N x sub n is equal to 0. Before it was always b sub n. I mean b sub 1. Now it's 0. B sub 1 is 0. And A12, I'm sorry, 21, sorry. Got to get my subscripts right. A21 x sub 1 plus A22 x sub 2 plus A23 x sub 3 plus dot 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 plus A sub 2 n x sub n is equal to 0. A sub 3 1 x sub 1 plus A sub 3 2 x sub 2 plus A sub 3 3 x sub 3 plus dot 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 plus A sub 3n x sub n equals 0. Get the idea. Everything's equal to 0. dot, 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 down to a sub m, 1, x sub 1. Let me make sure that, yeah, that's what they use too. Plus a sub m2, x sub 2, plus a sub m3, x sub 3, plus dot. Goodness gracious. This repetitive stuff drives me nuts sometimes, so I kind of just go all over the page with it. A sub m3, x sub 3, plus dot, 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 plus a sub m n, x sub n. That's also equals 0. So everything's equal to 0 everywhere. All of it pans out that way. Okay, that's what we mean by a homogeneous system of linear equations. All right. And as already noted, this always has at least one real solution. All the x's are 0. That's certainly going to make every one of those equations equal to 0 because there's no constants in them except 0. That's called the trivial, or sometimes called the obvious solution. Okay? Now, we're going to do something similar to what we did at example 8, but now going to do it with a homogeneous system. So I'm going to erase this. That's okay? All right. So here's our system. X sub 1 minus x sub 2 plus 3x sub 3 is equal to 0. 2x sub 1 plus x sub 2, and let me clean something up. My looking at this, I couldn't tell if that was plus or minus. It is a minus, but my pen drug a little bit. Oh, and here's Muhammad back. Okay, thought he had forgotten about us. Okay, welcome back. Okay. Hope you didn't throw your back out shoveling snow on Tuesday, did you?
It was so much snow.
So much snow, yeah, it was awful, wasn't it? But we lived through it, so we can tell the story to our grandkids. Okay, we're on example 9, page 21, section 1.2. Plus 3x sub 3, and this is equal to 0. What we're looking at now are systems of linear equations that are homogeneous systems, okay? Meaning all the constants on the right-hand side are zeros. And as we already noted, these are guaranteed to have a solution. x1 equals 0, x2 equals 0, x3 equals 0. That will always work because whatever you multiply by them, they're always going to add up to be 0. So you know these always have at least one real solution, okay? The question is, do they have any others? So we're going to do Gauss-Jordan elimination to see, okay? So first, what would be your augmented matrix here? 1, negative 1, and Daniel came in, so let me get him marked. Okay, middle part of the alphabet doing quite nicely. The top and bottom missing completely. Okay. Okay, next. 3, 0. Okay. Second line. 2, 1, 3, 0. Okay. Now, in Gauss-Jordan elimination, what's the first thing you want to happen? One in the upper left corner, you got it. Done. We didn't have to do a thing to get it. It was there already. What do we want to happen next? 0 beneath it. So how do we make that happen? Minus 2, row 1, plus row 2. That will do it. So we leave row 1 alone. 1, minus 1, 3, 0. And the new row 2 will be 0, 3. Negative 3. Ooh, 0. That's the nice thing about homogeneous equations, no matter what you do to them, that last column is always going to be a 0. Nothing can change it. Okay. All right. And Justin's here. All right. Now, what's the next thing you want to happen?
I think if there was a third row, we would want down to be also 0, 0, but...
Okay. Okay. First thing you want to happen? 1. We had it. 0 below it. Next thing you want to happen? 1. We want that 3 to become a 1. How do we make that happen? Divide the second row by? Divide the second row by?
1/3.
No, multiply by 1/3 or divide by 3. Yeah, either one. So I like to do row 2 divided by 3, or times 1/3. Same thing. Okay? So I think I'll write it down here. So the top row is 1, minus 1, 3, 0. Second row will be 0, 1, negative 1, 0. Okay? And then what's the last thing you want to happen? Say again? Not positive. Yes, you want that to be a 0. You want all the leading ones to be top to bottom by zeros. A 1 with 0 below it, a 1 with 0 above and below, but there's nothing below it, so just a 0 above. How do you make that happen? What's that?
Why do you want a 0 above it?
Why what?
Why do you want a 0 above it?
Okay, because this is what we call Gauss-Jordan elimination, which is you don't have to back substitute.
I thought it was you want the 0 to be below it and above it.
Okay, that's a Gauss elimination, and then at the end you do back substitution to get your equations above. This, doing a little more work here, you just isolate those leading ones. Nothing above or below except zeros. We'll see what happens, okay? So what do we do to get this to become a 0? No, that makes it a 1. To make that become a 0.
Divided by 0?
I don't think we can ever do that.
Then everything becomes 0.
No, divided by 0 is just not defined ever. You can never do it. Yeah. You can multiply by 0, but that wipes out all meaning of everything, so don't do either one of those ever, okay? Add the 2 rows together, and that will make that a 0, right? So row 2 plus row 1. That will do it.
So that would be the result for that would go back to row 1?
Yes, and that becomes your new row 1. Okay? So what does that become?
0. No, 1.
1, 0, second, 2, 0, and you leave the bottom row alone. 0, 1, minus 1, 0. All right, we've done our Gauss-Jordan elimination. We've eliminated all we can. That makes our third variable, x of 3, a parameter. You can use any value you want to. We can isolate what x1 is, isolate what x2 is. x3 can be anything. Okay? So, what do you want to let it be? Let x3 equal, just pick a parameter. Any parameter. Huh? Parameter of letter. A, that would be fine. Not what we usually use, but A is perfectly fine. So now this says, remembering where we came from, this says that x1, with a coefficient of 1, 0x2, plus 2a, your x3 was a, right, is equal to 0. So in other words, this is saying x1 is equal to minus 2a. Right? Subtracting 2a from both sides. Okay, but it's back, right? Okay, got it? So that's your x1. x2 from this one says x2 minus a is equal to 0. Because, this column is x1, x2, x3 constants, which are always zeros because they're homogeneous. So this implies that x2 is equal to a. And then we already know that x3 is, because of this minus 1 here, that's your coefficient. Okay. This is a row reduction of this, right? This is x1, x2, x3 constant. x1, x2, x3 constant. Let the x3 be a, because that's arbitrary here, whatever you want it to be. So then this one says x1 plus 2a is equal to 0, so that becomes a minus x1 equal minus 2a, subtract from both sides. This says x2 minus a, because x3 is a, and this is minus x3, so that minus a is equal to 0. So add a to both sides, x2 is equal to a, and here we have x3 is equal to a. So our ordered triplet solution, generic solution, is minus 2a, that's x1, x2 is a, x3 is a. There it is. Pick an a, any a in the world. 0, 0, 0, 0, certainly a solution, okay? Without a doubt. We knew that already. Okay, but pick any other solution. Pick an a, give me an a. 2, okay, that'd be minus 4, 2, 2. There would be a solution. Plug it in and see if it works. Minus 4, minus 2 would be minus 4 minus 2 would be minus 6, and then 3 times 2 is plus 6. That's equal to 0. The second one, 2 times minus 4 would be negative 8, plus 2 would be negative 6, plus 6 is 0. Okay? So yeah, pick an a, any a, plug it in, and that'll give you a solution. That's your arbitrary, infinite number of solutions. Not completely arbitrary. They have to be in this form, minus 2a. So your the y and z, or x2 and x3, always the same value, and x1 is always negative twice that value. That's how it works, okay? And that will be, what would it be, plane maybe, or something like that. Yeah. Okay. They used t and said x1 is minus 2t, x2 is t, x3 is t. A-t, whatever you want to call it, A-t and t, whatever you want to call it. Okay, it works. All right. Now, here's theorem 1.1, which is sort of based on that last example we did and this example. And here's the theorem. Every homogeneous system of linear equations, okay, is consistent. We saw that from before. You weren't in here when we said this. Is consistent. What does consistent mean? Has at least one solution. And 0, 0, 0, or however many variables you have, if every one of them is 0, it's called the trivial or the obvious solution. That will be a solution. So you know that every homogeneous system will have at least one solution, the trivial one. They may have more, okay? So, but every one is homogeneous system is consistent because it has at least one solution. And moreover, if the system, now here's the key for this one. If the system okay, has fewer equations has fewer equations than variables, I usually say it has more variables than equations, but it means the same thing. Then, if that's the case, then it must have infinitely many solutions. Okay, it must have infinitely many solutions. Now, at first glance, I really don't care for this too much because, wait a minute, what about your no solution case? We always had that as a possibility. And here we're saying if it's a homogeneous system and has fewer equations than unknown, have you lost completely the ability to have no solution? Well, yeah, you have. And here's why. Okay? Remember what gave you the no solution case? That's when you wound up with your bottom row was all zeros except for the last. And that was not zero. And that said that 0 times x1 plus 0 times x2 plus 0 times x3 is equal to negative 17. Or something. It can't happen. That's where your no solution case came from. But with a homogeneous system, you're guaranteed this is going to be all zeros. So even if you do wind up with a row of all zeros at the bottom, then that one will be 0 too, and that's an infinite solution case. So sure enough, this is correct. You will have infinite solutions. If you have more, if it's a homogeneous system, more variables than unknowns. Sorry, I said the same thing. More variables than equations, then you are going guaranteed to wind up with infinitely many solutions. Okay? No way around it. You won't have just a trivial case. You'll have infinitely many solutions. Now, some others you could have just a trivial case, but not this one. Okay. That finishes, finally, 1.2. Homework exercises here. Do any of the odds 1 through 5. Do either 7 or 9 or both. Do any of the odds 11 through 17. Excuse me. Any of the odds 19 to 23. Any of the odds 25 to 29. Nope. 25 through 37. Do 39. It's sort of long. Give it a shot anyway. If it gets too tedious, you can stop it. But, you know, at least get the idea and get going on it. Then for homogeneous systems, do either 41 or 43 or both. Then there's a applied problem number 45. Excuse me. A finance problem. And then 47. Okay. No, this is okay. Try to do 47 and try to do 49. Okay. Try to do 50. 53. 55 you can look at, think through. If you want to write something, you can, but that probably doesn't have an answer in the back. 57 is a true-false, so you can take a look at that. 59 is a writing exercise. You can think through that if you want to. 61, now, this book does this periodically, and it kind of grates on my nerves, okay? They give a definition in the problems. They haven't discussed it in the text, but they give the definition in problems and then give you exercises in it. So this is, they're now telling you no, I'm sorry. This is okay. It says determine the conditions for A, B, C, and D such that the original matrix A, B, C, D will be row equivalent to the number 61. So you should be able to do that, no problem. I was thinking something else. And here now, number 63, they introduced the concept of having some lambdas in there. Now, I know where they're going on it, okay? Later in the book, we'll hit eigenvalue and eigenvector problems, and these are related to those. So they're getting you used to it now. We may or may not get there later, but anyway, you can get used to it. Play around with 63 if you'd like. 65 is a writing problem, and 67 is, so you can look at those if you want to and see what's there. So let's move on to 1.3. Any questions on 1.2? Okay, 1.3 is applications of linear systems. All right, now, I think what I'm going to do is kind of go through this rather quickly without getting too bogged down with it. In fact, I think there's been some times in the past I've actually skipped this, but I think because sometimes these can get a little tedious, okay? Some of you already had your physics, right? And all of you have? You have, okay. So some of this will be reviewed from physics. Not much, but a little bit will. But it just shows some various applications for linear equations. The first of these is what they call polynomial curve fitting. Okay? Now, excuse me. If you have 2 points, can you get an equation that will go through both of those points?
Yes.
Yeah. What kind of equation will it be?
Well, it can, at the minimum, be linear. It can also be exponential order because there's 2 points.
Is what?
If it's 2 points, then any equation of a line will work.
Exactly. Well, yeah. It's one particular line, okay, but a line will work. A linear equation will connect those 2 points. Now, what if we had 3 points that were not collinear?
At minimum, you would need an exponential, but you would need some higher order.
Okay. And what would be the minimum that would work?
The minimum would be quadratic.
Quadratic, exactly. What if we had 4 points? Non-collinear.
Quadratic might.
Might, but it wouldn't be guaranteed to. To be guaranteed to get it?
Third order.
Third order.
Yeah.
Okay, you get the pattern? However number of points you have, you can guarantee it can be fit exactly with a polynomial of n minus 1 order. Okay. Yeah, that's the point here. Now, if those 3 points were collinear, then a straight line will still work. And if that 4th point happened to fit on the same parabola that the first 3 define, then yeah, then the parabola of the quadratic would work. But let's assume that these are not that closely related, okay, that they do require another degree to make them work, okay? So here is a supposition here. Suppose n points in the xy plane, that would be x1, y1, x2, y2, x3, y3, ... up to and including x sub n, y sub n. Okay. You have these endpoints on the xy plane. They represent a collection of data. You're asked to find the polynomial function of degree n minus 1 that fits those data. And you can do it. You may be able to find one that's lower degree, but you definitely can find one of n minus 1 degree. Okay? We just sort of solved that by the dots out there, okay? Now, and that'll be a polynomial of degree n minus 1, okay? Because my nose is itching like crazy. My mother used to say that means you're going to have company. So I don't know what that means, but I just can't stop scratching my nose. It's just itching. Okay. Now, it says that, okay, here's what it is. Okay, trying to find where we were. You come up with a polynomial as a function of x, okay? And you know this is going to be true. A sub 0 plus a sub 1 x plus a sub 2 x squared plus a sub 3 x cubed plus dot 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 plus a sub n minus 1 x to the n minus 1, okay? That is your polynomial of degree n minus 1, and you claim that all those points can be fit by that polynomial, okay? Well, if that's the case, then start here. A sub 0 plus a sub 1 x1 plus a sub 2 x1 squared plus a sub 3 x1 cubed plus dot 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 plus a sub n minus 1 x sub 1 to the n minus 1. That's going to equal y1. Because this is your function of x1, and when you plug that in, y1 is going to be your result. Okay? And then do the same thing for x sub 2's. And that will be y sub 2. X sub 3 will be y sub 3. And you just keep proceeding this way. A sub 1 plus, a sub 0 plus a sub 1 x sub 2 plus a sub 2 x sub 2 squared plus a sub 2, a sub 3 x sub 2 cubed plus dot 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 plus a sub n minus 1 x sub 2 to the n minus first, and that's equal to y2. That's plugging this value. The first equation plugged the x1s in and got your y1. Second one plugged the x2s in and got your y2. Third one would be a sub 0 plus a sub 1 x3 plus a sub 3 x sub 3 squared plus a sub 4, wait, I messed up. I skipped 2. Okay, a sub 3 x sub 3 cubed plus dot 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 plus a sub n minus 1 x sub 3 to the n minus 1. 3 is equal to y3. And these continue dot 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 down to a sub n minus 1 x, oh, I didn't write my last line, a sub 0 plus a sub 1 x sub n plus a sub 2 x sub n squared plus a sub 3 x sub n to the fourth, no third, goodness gracious, okay, plus dot 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 a sub n x to n minus 1, minus, x sub n minus 1 raised to the n minus 1, and this is equal to y to n minus 1. No, y to n. Okay. x sub n raised to the n minus 1. All right, finally. Okay. Whew. Okay. Because if this polynomial of degree n minus 1 is going to fit every one of those points, you can plug all the x's from that point in, and then that will equal your y. Say for x1, so it'll be y1, x2 is y2, x3, x sub n, y sub n. Okay. Let me make that look a little nicer. Okay. Okay. I think that looks as nice as I can make it. Okay. Yeah, I did mark this one. Okay. Now, that's an n minus 1 degree polynomial with n different points. What a pain. Let's get it down to something simpler, like a second degree polynomial with three points. Excuse me. Got the hiccups. All right. Determine the polynomial p of x, which is equal to a sub 0 plus a sub 1 x plus a sub 2 x squared. Okay? Whose graph passes through these 3 points. 1, 4, 2, 0, and 3, 12. Okay? Now, 3 points. You want a polynomial of degree 2, 1 degree less than the number of points you have, that'll work. Okay? Well, then we know that P of 1 will be a sub 0 plus a1 times 1 plus a2 times 1 squared, and that's equal to 4. We just plug in 1 for the x's and have it equal to the y. So there's your first equation. P2, P of 2, would produce this equation. A0 plus 2a1 plus 4a2, I'm plugging in 2 for x, and that's equal to 0. That's your y value. And P of 3 would be a sub 0 plus 3a1 I messed up no, I didn't. Okay, it was fine. No, yeah, okay. Yeah. Plus 9a2 is equal to 12. Okay. I'm reversing the order of the x's and the a's, and I was getting confused in doing so. All right. 3 equations, 3 unknowns. Can we do this?
Looks like it.
Sure. Gauss-Jordan elimination. So let's first write this as an augmented matrix. And what would that be? 1, 1, 1, 4. Right? Next. 1, 2, 4, 0. Next. 1, 3, 9. You're making fun of my writing. I understand, but I'm not hurt at all. No, it doesn't bother me much. Okay. For you to make fun of my writing. Okay. So, there we have it. Now, Gauss-Jordan elimination. Is that what you want to try? What you want first? 1 in the upper left, we got it. What you want next? 0's below it. So how do we get a 0 instead of that second 1 there? Minus row 1 plus row 2 is a new row 2. Okay? So row 1 stays the same, 1, 1, 1, 4. Row 2 becomes 0, 1, 3, and negative 4. That's a 4 up top. Again, making fun of my writing, I can tell. Next, negative row 1 plus row 3. And what would that be? 0, 2, 8, yeah. That would be 8, wouldn't it? Right? I was kind of doing this in my head, and my head's clogging up, so I'm having trouble breathing. All right. Now, what's next thing you want? Okay, you want a 1 in first non-zero entry in row 2 to be a 1, and then you want 0 above and below it. But frankly, to make that happen, just to get your numbers down, let's divide everything here by 2. Because it's doable, really easy. So let's just make this a 1, 4, 4. 1, 4, 4. Okay, 0 in front. Okay, so that's our new row 3. Not going to help us a lot, but it will help a little bit. Okay, so how do we get a 0 above that leading 1 in row 2 in column 2? Negative row 2 plus row 1 becomes your new row 1. So we're going to leave row 2 alone, 0, 1, 3, negative 4, and do a new row 1. What would that be? Not negative 1, 1. Minus row 2 plus row 1. Yeah. Okay? Next. Whole reason we did it. 0. Perfect. Next. Negative 2. Next. 8. Negative row 2 plus row 1. Okay? Got it or not? Got it? Okay. Now what do we want next? That 1 below to be a 0, and how do we make that happen? Negative row 2 plus row 3. It's not a row 4, it's row 3. And that gives you 0, 0, 1, is that right? Yeah. Okay, what's the next thing you want to happen? You got a 1 here, 0 below it, 1 here, 0 above it below. You want a 1 here. Hey, we got it. Don't have to do a thing to get that. But now we want 0 is above it. So what's going to be our first step? Second? For this one? Then you mess up your leading 1. You don't want to do that. What you want to do is use your third row, multiply by something, add to this to make a 0. Right? It's the opposite of that number. 2 row 3 plus row 1. You see? Okay? And when you do it, because of your judicious way of doing it, we're using row 3 now, so we'll write that down, 0, 0, 1, 8. And by the way, if we were doing Gauss elimination, we could stop right here and say A2 is equal to 8. Plug in an 8 here and then subtract and stuff like this. You can do back substitution. But Gauss-Jordan elimination will eliminate these two without too much pain. And then all you have to do is plug in. So let's see. The top row becomes, it's 2 row 3 plus row 1. No? 1, 0, 0, that's why we did it, and 2 times row 3 plus row 1. Isn't that 24? Seems like an awfully big number. Yep. That's right. Okay. Next, how do we get the 3 to become a 0? Negative 3 row 3 plus row 2. Always use the leading one, and that's in row 3. Okay, so what would it become? 0, 1, 0, whoa, wait, I'm sorry. Whoa. I was looking at the wrong thing, sorry. I thought that doesn't seem right. Okay. That'd be minus 24 plus 4 is minus 20, right? No. Minus 28. Goodness gracious. Suddenly the brain quit working. I don't know what happened here. All right, let's do it again. Minus 24 minus 4 is minus 28, right? Yeah. Minus 3 times 8 is minus 24, minus 4 is minus 28. Yeah. Whew. So here what we have, a 0 equal 24, a 1, that's what the second row represents, column represents, is equal to minus 28, and a 2, that's what the third column represents, that's equal to 8. So what does that mean? Here's our polynomial. P of x is equal to 24 minus 28x plus 8x squared. Now, all you have to do to check this is plug in the, for x, plug in a 1, and you get 24, oh, yeah, okay. 24 minus 28 is minus 4 plus 8, be plus 4, and sure enough, your y is plus 4. Plug in a 2, and you get 24 minus 56, that would be a 32, plus 32, which is 4 times 8, is 0. Yes. And then plug in a 3, 24, oh goodness, that's too big. Pull out your calculator. 3 times 28, is it 84? Huh? 84. So minus 84, 24 minus 84 is minus 60. Yeah. Plus 8 times 9 is 72. Yeah, 72 minus 60 is 12. Yes, that works. Those 3 points will fit on that polynomial, quadratic equation. Okay? All right. And they show the graph here, and sure enough, it does fit. All 3 points perfectly. Okay? Example 2 is now 5 points. How are we doing on time?
It is currently 12:42.
Okay, and we're supposed to go till 3 minutes. Don't think we're going to get a 5-pointer done, do you?
No.
Okay. Actually, it's not as bad as what you might think, but it will take more time than what we've got now. So let's just mark that for where we begin next time, and let me erase where I had marked the time before. Okay? So homework exercises here for this section will be, this is one long section. I know you can do 1 and 3. You can try 5 if you want to. Okay? It really won't be as bad as you might think. And actually 7 won't be as bad as you might think either. But we've only done 3s, so 1 and 3 will certainly work. I think you'll find 5 works fairly easily too, but you don't have to do it if you don't want to. Okay, I'm going to try to speed through these a little bit faster. The polynomials do take a while, and maybe some of the others we won't do in gory detail. I do want to do probably network analysis, because I think some of you probably will need to do that, and then electrical networks in particular, because I know you've probably already done those. Okay.
I haven't started most of the electrical stuff yet, but it does sound familiar.
What's that?
I haven't started much of my electrical stuff yet, but it does sound pretty familiar.
Yeah, you will definitely get familiar with it. Okay, so we'll end it there, and let's have no more Tuesdays off, okay? This gets to be sort of sad. Okay.